This video will discuss matrix commutators of Hermitian matrices. So in general, let's say we have some matrix A, some matrix B. These are both n by n Hermitian matrices, the same number of dimensions for each of them. They're both square and Hermitian. So we have this symbol where we have a bracket A, comma, B, close bracket. And this is defined as A times B minus B times A for matrix multiplication and then matrix addition for the two of them. And the resulting value will be a matrix. So matrix times n by n times n by n matrix gives you an n by n matrix. Similarly, n by n times n by n gives you an n by n matrix. N by n matrix minus an n by n matrix gives you an n by n matrix. So that n by n matrix is called the commutator of A and B. A and B will only have a commutator if they're both of the same, if they're both square and they both have the same number of elements. Similarly, the less commonly used but shows up in a few places in electronic structure theory, we have these curly braces, A, B is equal to A times B plus B times A. That is called the anti-commutator. But most important for our purposes is going to be the commutator. So if the commutator of A and B is equal to a zero matrix, so a matrix where all the elements just end up being zero, if they're equal to a zero matrix, then A and B are said to commute. If A and B commute, then with the same unitary matrix that you can diagonalize A, you can also diagonalize B. So A and B here, in this case, are both diagonal matrices. The elements of them are 0 unless I equals j. So what does this mean? So from the previous video, we looked at matrix diagonalization. We showed that diagonalizing A with a unitary transformation gives us the elements which are all eigenvalues of A. So A, the value aii is the ith eigenvalue of matrix A. Similarly, B, in its diagonal form, is just a list of the eigenvalues of B down the diagonal. And we said that U is a matrix which is all of the eigenvectors of A. So U is also a matrix which is the eigenvectors of B. So if their commutator is 0, then they have basically the same eigenvectors. If they have the same eigenvectors, then we can know both of their eigenvalues simultaneously and exactly, because knowing the eigenvalues of a given matrix comes down to being able to diagonalize it. So if they commute, then they get diagonalized by the same matrix. They have the same set of eigenvectors, and we can know the eigenvalues of A and the eigenvalues of B exactly at the same time. If they do not commute, then there exists what's called an uncertainty relationship between A and B. Because if they don't commute, then this matrix U is going to be different for A and B. Thus, they're not going to be completely diagonal at the same time. There will be some off-diagonal elements. Now, we said in previous videos that the trace of a matrix is equal to the sum of its eigenvalues. So you still have some clue about what the eigenvalues of both of them are, but you don't know them both exactly. So taking a unitary transformation here is kind of somewhat equivalent to, say, kind of measuring what the eigenvalues are, measuring what those values are. And if we try to do that to both of them at the same time, then we can't get them both exactly when there's that uncertainty relationship. So for example, the matrix representation of position and momentum in quantum mechanics, they don't commute. There is some non-zero value in the commutator. So that's why there's an uncertainty that exists between the two of them, because we can't diagonalize both operator matrices simultaneously. So that's not just for position and momentum, that's true for any two operators, any two measurable properties where the matrix representations of them don't commute. There will be some kind of uncertainty relationship between the two of them, and that you have to pick one over the other if you want an exact measurement of those values.